Hello everyone, this is Professor Santosh Tondare and I welcome you all. In this segment we are going to discuss about properties of Fourier series. Friends, in the previous segments we have seen how to find Fourier series coefficients of continuous time signal as well as discrete time signals. If you are new to our channel, please do subscribe for latest updates and you can go and click on the previous lectures also. Now, as far as properties are considered, we are going to see basic 5 to 6 properties, starting with linearity, time shifting, time reversal, time scaling. Then it is multiplication property. Then we are having complex conjugate properties, and the structures are going to be same. Only the formulas are going to be different. As far as the first property, which is called as linearity property. Now, we have already seen a definition of what is meant by linear system. So, a system which satisfies superposition principle. That means weighted sum of input should be equals to output due to weighted sum of input terms. If this condition is satisfied, the system is said to be linear system, and the property is called as linearity property. Now in this case, I have taken two components of x of t as x1 of t and x2 of t. We know that if we have an input signal x of t whose Fourier series coefficient is ak, then if I take its combination as linear combination, its Fourier series becomes linear combination of output signals as a, x1 of t is Fourier series coefficient ak1, x2 of t is ak2. Now in order to prove this property, we should make use of these two fundamental formulas of Fourier series. The first one is for Fourier series representation and this one is for Fourier series coefficients. Now in this case, in order to prove this property, we'll use this particular fundamental formula as Fourier series coefficients of the given signal, which is x of t, is written by the formula as ak is equals to 1 upon t integration. This is our input signal x of t into its exponential term, this one. Now instead of x of t, we are using linear combination of input signal, which I can turn out here, and this becomes 1 by t integration a x1t plus b x2t, and now this is multiplied with exponential term as e raised to minus jk omega naught t. Once it is over, we'll move on to just splitting the terms. I can multiply individual term with exponential terms, so this becomes, I'm writing it directly now, a as it is into 1 by t integration x1t with exponential term, this one dt is element into dt. Similarly this term as b into 1 upon t integration, this is x2t into exponential with its dt. Now if you look at this particular formula, which we have already been written, ak is equals to this one. Now if instead of x of t, if we are getting x1 of t, this becomes ak1. Similarly if it is x2t, it becomes ak2. So based on that, I can write this term as a ak1 plus b into ak2, and this is what called as the linearity property. Weighted sum of input is equals to output due to weighted sum of input terms. Remember friends, the same technique we are going to use for Fourier transforms, Laplace transform as well as for set transform. Only the formulas are going to be changed. Now we'll move on to the next property, that is called as time shifting property. Here the statement, if we have input signal x of t whose coefficient is ak, then if I shift input signal by certain delay as t naught, the same should be replicated in its Fourier series ak into its exponential term. Now to prove this property, we'll go for finding its Fourier series coefficient. I am writing Fourier series coefficient of x of t is, we have that formula as ak 1 upon t with its integration, input signal as x of t, into we have the set as e raised to minus jk omega naught t into dt. Now we will add a delay of t naught in the input signal, so add delay of t naught in input signal. This equation holds 1 upon t, that integration remains same. Now this becomes x of t minus t naught into exponential term as it is. Now in order to proceed, we need a single variable term over here because input signal should be unique one. So I can substitute t minus t naught as m. So t becomes equals to m plus t naught, and if I take this differentiation term, differentiating on both the side, will get dt is equals to dm, because t naught is constant and differentiation of t naught or any constant term is 0. So once you replace all these values here, this equation holds 1 upon t integration x of m into e raised to minus jk omega naught. Instead of t, we will put this value as m plus t naught into dm. Now this integration is with respect to m. Now if you split this term 1 upon t, this integration xm into e raised to minus jk omega naught into m multiplied with this term e raised to minus jk omega naught t naught into dm. Now if I take this term outside, probably we can write the same integration xm e to the power jk omega naught m dm multiplied with e to the power jk omega naught into t naught. Now if you see this particular equation, it is nothing but our Fourier series coefficient, and based on that we can write this term as ak multiplied with this term. So this is called as the second property as time shifting property. Now we'll move on to the next property, which is called as time reversal property. Here the first statement is as it is, x of t be any signal whose Fourier series coefficient is ak. Now we have to reverse this signal, so we can write then we have to find Fourier series of x of minus t. Actually the value should be minus a suffix minus k, but we should prove this one. So in case of that, directly we will call the same term Fourier series coefficient of this particular function x of minus t is the same formula we'll use, 1 upon t integration x of minus t exponential term into dt. Now here we have minus t, but we need a single variable term, so again we'll go for the same method. Let minus t is equals to m, t becomes equals to minus m. If we differentiate on both the side, we'll get dt is equals to minus dm. Now we'll put all these values in the given equation. This becomes 1 upon t integration, this is xm e raised to minus j k omega naught. Instead of t, we'll write minus m, and instead of dt, we'll write minus dm. Now I can take minus sign outside, minus remaining term 1 by t integration, this is xm exponential e raised to minus j. Now this minus sign I can give it to k also, because they are in multiplication. So this becomes minus k omega naught m into dm. Now if you analyze this particular equations or this particular formula that we have, if k is positive, its Fourier series coefficient is positive, and in this case k is negative, so this formula becomes minus a suffix minus k, and that is known as what? Time reversal property. In order to prove these properties, remember we have to follow 3 steps. Number 1, the basic formula. Second is substitution method, or just we have to assume some constant term. And third, we have to simplify. Dear friends, in order to prove properties of either signal and systems or properties in terms of digital signal processing, just follow these 3 steps. Put the formula, required formula, go for the substitution method, and simplify the given terms. Now we'll move on to the next property, which is called as time scaling property. Now maybe in unit number 1, operations on signals, we have seen such kind of operations. Now in case of time scaling property, we should multiply the time period with some factor which is called as time scaling factor. Let us consider it is x of beta t. That means it is multiplied with beta factor, and its Fourier series coefficient we have to find. Now in case of time scaling operation, remember the trick, just divide the output signal by the given time period or by the given time scaling factor. Now here we have the Fourier series coefficient a k, so I will divide it by beta factor, and this entire term will again divide by beta. In case of unit number 1, introduction to signals and systems, we have performed certain operations. In that we have time scaling operations. So whenever we time scale any input signal, it results into 2 forms. Either the signal will expand or the signal will compress. So it depends upon whether we are dividing with integer or fraction. Now let us prove this property. Again we'll use Fourier series coefficient of, we have the input signal x of beta t is, so we have that formula. This is 1 by t integration, input signal is x of beta t multiplied with exponential term into dt. Now again second step, just substitute this. So we'll write let beta t is equals to m. So if beta t is equals to m, we'll get t is equals to m upon beta. If I differentiate on both the side, we'll get dt is equals to 1 by beta into dm. Now if you put all these values here, we'll get this integration term 1 upon t integration, this is x of m into e raised to minus jk omega naught. Instead of t we'll write m by beta, instead of dt we'll write dm upon beta. Now we'll take this beta outside, so this is 1 upon beta, remaining whole terms as it is 1 upon t integration, this is x m into e raised to minus j. Now I am doing this adjustment. These entire terms are in multiplications, so we can write this as k by beta into omega naught into m. Now again the same formula. If it is k, this becomes Fourier series coefficient ak. If it is k by beta, definitely this becomes 1 by beta into a of k by beta. This is what we have to prove as time scaling property. So we'll move on to the next property, that is called as complex conjugate property. Now here the first statement as it is, now we have to take complex conjugate of the input signal. So I can take this as x complex of t, and we have to determine its Fourier series coefficient. Now just we'll put here a question mark, that we didn't know anything about complex conjugate, only the term is that input should be taken as complex conjugate. So here to prove this formula, again we'll go for the same steps. Number 1, the complex conjugate of x complex of t. So I'm writing this formula ak as 1 upon t, this is our input signal x so t into e raised to minus jk omega naught into t. Now we have to take its complex conjugate, so whenever we'll take complex conjugate, this becomes x complex of t into e raised to, now this minus j becomes plus j into dt. Now why we are treating this as plus? Because if we have a complex number x plus iy, its complex conjugate becomes x minus iy. That means there will be a sign change of imaginary term only. Here minus j was there, so its complex conjugate becomes plus j. Now in order to simplify this, we have a standard formula that it should be written in the form of what? Minus j. So I can make this adjustment, 1 upon t is integration x complex of t. Now in order to fetch exponential minus, I am writing this as minus j. Instead of k, I am writing this as minus k omega naught t into dt. Now why this adjustment is there? Because we have to use the same formula, and this minus minus again becomes plus, so we are getting the same equation, only we are rearranging the term. Now this is complex, this is minus k, this means this entire signal becomes a complex conjugate. If it is plus k, we should write plus k, but now we are having minus k, so this becomes a suffix minus k, or a complex of minus k. So this is called as complex conjugate property. If it is there, we will move on to the next property, that is called as Parseval's relation. Here it is, our next and important relation, that is called as Parseval's relation. Now it simply says that if we have x of t and ak as a Fourier series pair, then 1 upon t integration mod x of t square dt becomes equals to summation ak square. Parseval's relation is basically useful in order to analyze the given signal as energy or power signals. Now we are using the same set of equation. This is in continuous and this is in discrete form. So in order to prove this, we'll take the LHS term, which is given as 1 by t integration this entire term as it is x of t square into dt. Now if you see this one, this is mod x of t square. I can write mod x of t square in a form of real number with its complex conjugate multiplication as x of t multiplied with x complex of t into dt. Okay, if it is there, we'll look after RHS. In RHS we have to add one summation term, or just we have to go for a summation term, and in order to get the summation term, we have a standard formula that I can use, which is called as Fourier series representation, x of t as summation a k into e raised to j k omega naught t. Okay, so we'll replace either x of t or x complex of t with this particular formula. I will adjust it with x complex of t. So this becomes 1 upon t integration as it is. This first term will keep as it is, x of t into x complex of t. So this becomes summation. Now this k term as it is, ak exponential and its whole complex into dt. Remember, this is x complex of t, this is an entire term, so its formula will be written as this or this complex conjugate. Now I will give this complex sign to the entire term, so that this holds 1 by t integration x of t summation a complex of k. Now if I give this complex sign to exponential term, plus j becomes minus j into dt. Once it is over, now the next step, just we have to adjust the given terms. I am taking this summation outside, summation this complex term a complex of k. Now the remaining terms, 1 by t integration x of t and this exponential term as it is. Now if you look at this particular formula, this is nothing but our Fourier series coefficient. So this holds summation a complex k into ak. Now if you see the first step, mod x of t square was written as x of t into x complex of t. Similarly, ak into a complex of k can be written as mod ak square. So this term is called as Parseval's relation. I hope you understood the basic 6 properties of Fourier series. Thank you.